Okay, so that was the linear support vector machine in the previous session. Now we're going to do the nonlinear support vector machine. And again, when fitting the support vector machine, the cost parameter is a tuning parameter that one would normally have to select. We're not going to do that in these sessions, but you can use cross-validation to select that. And that's done in the R sessions in the book, but we're not going to do that. So what we're going to do here is actually take an example from their more advanced textbook, Elements of Statistical Learning, which had a canonical example of in two dimensions where the decision boundary was nonlinear, and we're going to use the kernel support vector machine to try and learn that boundary. And so we're going to use that example. So we can actually get the data for that example from the Elements of Statistical Learning book. And you can see here, we've got a load command, and we're going to load directly from it a URL, which is the web page where these data live. And so you can see the URL, and the data is the mixture data. It's simulated data. And so here you see how to read data directly from a website. Okay, so the data is loaded, and now we can say names, and we see that this is actually a list, these data. It's got a number of components. For the moment, the training data are X and Y, and there's some other variables on there which we'll get to in a moment. Now, first of all, we've already created an X and Y for our previous example, so I'm going to just get rid of those so that I can attach this data, this list, which I've now done. So let's plot the data, and there they are, two-dimensional data. They seem to overlap quite a bit. But we'll see that there's something special in the structure of these data. We'll make a data frame with the response y, and we'll turn that into a factor, and just much like before. And now we'll fit a support vector machine. But here the kernel will be radial, and we'll give a cost parameter of 5. And again, we won't scale the data. Okay? And so that's fit. And so now we're going to create a grid as before and make predictions on the grid. Now these data actually came supplied with grid points. If you look down on the summary on the names that were on the list, there's two variables, px1 and px2. And so these are a grid of values for each of the two variables. Okay? So we don't actually have to use our function that we created. We can just use expand.grid directly to create the grid of values. And so we do that. And like before, we'll predict the classification at each of the values on the grid. And now we'll plot and include the points, color the points according to the decision boundary. And wow, look at that. So you can see the decision boundary is nonlinear now. And it's the red points are the red regions largely to the top, and the black regions largely down below. We can put our data points in the plot, and we see where the data lies. And you can see that the decision boundaries, to a large extent, follow in where the data is, but in a very nonlinear way. Okay, let's see if we can improve this plot a little bit further. We'd actually like to put in a curve that gives the decision boundary. And what we're going to do that is we're going to use the contour function. Okay. On the data data frame is also a variable called prob, and prob actually gives these data were simulated, and prob gives the true probability of a +1 versus a -1 at every value on the grid that we have here. Okay. So we can do two things. We're going to use the contour function, and we're going to plot the contour of prob at a half, which would be the true decision boundary for these data. And then what we're going to do is we're going to predict from our model. We're going to predict not just the class label, but we're going to predict the function itself, and we'll get the decision boundary that's learned for these data by plotting the contour of that function, the zero contour, because that function we classify to +1 if it's positive, otherwise to -1. And so we're going to do that for each of these and include them on the plot. Okay? So The first one is we'll just predict our fit on the grid, okay? But we tell it decision values equals true because we want to get that function, the actual function, and not just the classification. And the way it returns it as an attribute of the actual classified values. So we have to pull off that attribute. And so we use the attributes function that pulls off all the attributes, and then we access the one called decision. And so now we have the function that we want. And once again, we have our grid. Actually, we'd made it already. We wasn't need to make it again. And we've got our classification again. So now we make the same plot as we had before. We add our points again. And now we'll make a contour. And we use a contour function. And it requires those two grid sequences as well. And then it wants the function you want to contour in the form of a matrix. And if you look at the dimensions of px1 and px2, you'll see they're 69 and 99. And this function, we're going to contour at level 0, and we're going to add it to the plot. And sure enough, you can see that tracks the decision boundary. So that's a really handy way of plotting a nonlinear decision boundary in 2 dimensions. And finally, we include the truth, which is the contour of the probabilities, which we're going to, that's the 0.5 contour, which would be the decision boundary in terms of the probabilities. And so that's the true decision boundary, or what's called the Bayes decision boundary. So that's the ultimate one. If we had large amounts of data, we'd hope to be able to get very close to that. But you can see our nonlinear support vector machine has got pretty close to that, especially in the regions where we've got data. And so here we've seen how to include these nonlinear boundaries in the plots. Okay, so we've finished this session. So once again, we were using R Markdown, and where we've mixed actual text with our R commands. The 2 sessions on SVM are like that. And at the end of it all, we can use the function knit, and it runs through all the code and produces a nice web document that summarizes all that we've done. This is something you can share with your colleagues. You can display it. You can put it on your own website. Puts all the figures in, and and shows exactly what you've done, and all the plots, everything that we produced in somewhat nice quality as well. And so this is a document that you can save and distribute.